Hi everyone, good evening. This is Dr. R.S.ALAMELU, Associate Professor and Head, PG Department of Applicable Mathematics. Welcome to the lecture on Calculus of Variations. In today's video, we are finding the examples of certain type of variational problems. By substituting the Euler's equation. So now we recall the standard type of functionals and a very basic functional v of y of x is equal to integral x naught to x1 f of x comma y dash into dx with fixed boundary points y of x naught is equal to y naught and y of x1 is equal to y1. Hope you all remember how to solve this type of functional. We obtain the Euler's equation. What is that? Fy minus d by dx of fy dash equal to 0. What's our Fy stands? Dou f by dou y. Yes. And what's our Fy dash? Dou f by dou y dash. Fine. See, functional is functions with one or more variables. So now we extend one more variable. So of the type v of y of x comma z of x, which is integral x naught to x1 f of x comma y of x comma z of x comma y dash of x z dash of x into dx. With the boundary conditions, y of x naught is equal to y naught and y of x1 is equal to y1, z of x naught is equal to z naught, z of x1 is equal to z1. So how do we solve this? Again by applying the system of Euler's equation. What are they? Yes, Fy minus d by dx of Fy dash equal to 0, right? Another equation? Yes, Fz minus d by dx of Fz dash equal to 0. Now let us see some examples of these type of functionals by applying the Euler's equation to find the extremals. Are you ready? Good. So now consider the functional v of y of x is equal to integral 0 to pi by 2 y dash square minus y square into dx with the boundary condition y of 0 is equal to 0, y of pi by 2 equals to 1. So now how do we start with? So what is this general type? V of y of x is equal to integral x naught to x1 f of x comma y dash into dx. Here the limits are 0 to pi by 2. So let us take our f as y dash square minus y square. With the boundary condition y of 0 is equal to 0. What does it mean? When x is 0, y is 0, right. When x is pi by 2, y is 1. So now apply the Euler's equation Fy minus d by dx of Fy dash equal to 0. On substituting we get, what's our Fy? Minus 2y. What's our Fy dash? 2y dash. Then by substituting in 1 we get minus 2y minus d by dx of 2y dash equal to 0. So we can rewrite it as y double dash plus y equal to 0 because your minus 2 cannot be 0. Now we have to solve this differential equation. Yes, how do we solve it? So apply the auxiliary equation and find the complementary function. We get y is equal to c1 cos x plus c2 sin x. So what's the next step? We need to find the constant values. So how do you find the constant value? We must apply the boundary conditions, right? Okay. So what are the boundary conditions we have? It's given in the problem. So in applying these boundary conditions, we get y is equal to sin x is a extremal. That is, we obtain the value for c1 as 0 and c2 is equal to 1. So on substituting in y, we get 0 into cos x plus 1 into sin x, which is y is equal to sin x. So that's the extremal. So for this functional, the extremum is attained on the curve y is equal to sin x. Is it clear? Fine. So now, are you interested to see one more example? Good. We can solve the problems under the second type of functional, that is we have one more variable z along with y. So what is the standard type? y of x comma z of x, which is equal to integral x0 to x1 f of x comma y dash z comma z dash into dx. So in this type we have a problem. So let's solve this extremal of that type y of x comma z of x. What is it? Integral 0 to pi by 2 y dash square plus z dash square plus 2 yz into dx. Here what are the boundary points given? Y of 0 is equal to 0, y of pi by 2 equals to 1, z of 0 is equal to 0, z of pi by 2 is equal to minus 1. So now obtain the system of Euler's equation fy minus d by dx of fy dash equal to 0, then fz minus d by dx of fz dash equal to 0. Do remember we are substituting the Euler's equation to find the extremals. Now what is our f? Y dash square plus z dash square plus 2 yz. So you know how to find fy dash, fz, fz dash. On substituting in the Euler's equation, we have these two equations. What are they? Y double dash minus z equal to 0 and z double dash minus y equal to 0. So now write one in terms of the other. Okay. So I am taking z as y double dash. So what do you get? On substituting in the second equation, we have y power 4 minus y equals to 0. So again, we need to solve this differential equation. So write the auxiliary equation, which is m power 4 minus 1 equal to 0. Then rewrite it, m square the whole square minus 1 equal to 0. So what is it we have? M square minus 1 into m square plus 1. This is m square plus 1 equal to 0. So here m is equal to plus or minus 1 and plus or minus I. So we have the solution y is equal to c1 e power x plus a e power, normally what is it? A e power m1x, two distinct roots, a e power m1x plus b e power m2x, and then for real and imaginary, e power alpha x into a cos beta x plus b sin beta x. On substituting this, we have the solution y is equal to c1 e power x plus c2 e power minus x plus c3 cos x plus c4 sin x. And what is the next step? We have z also. What is your z? Y double dash, right. So find the second derivative of y, that's your z. So you know how to find it, y dash and y double dash. Fine? Okay. Next, on substituting the boundary conditions, we need to get the constants c1, c2, c3 and c4. Okay. So apply the boundary conditions. What are the boundary conditions we have? Recall the boundary conditions. What is given in the problem? Y of 0 is equal to 0, y of pi by 2 equals to 1. Z of 0 equal to 0, z of pi by 2 equals to minus 1. What does it mean? When x is 0, y is 0. When x is pi by 2, y is 1. When x is 0, z is 0. When x is pi by 2, z takes minus 1. So on substituting these conditions, we get the constants c1, c2, c3 and c4. So here we obtain c1, c2, c3 as 0 and c4 is equal to 1. Substituting these values in y and z, we obtain y is equal to sin x and z is equal to minus sin x. So the function attains extremum on the curve y is equal to sin x and z is equal to minus sin x. Is it clear? Good. Thank you.